Welcome back to the deep dive. Today, we are looking at something you probably see on, I don't know, half the labels in your kitchen, but just skim right over.
Mm.
We are talking about citric acid.
It really is the invisible architect of so much of our modern food. We see it on the label, or maybe it's its E number, E330.
A330. It just sounds so industrial.
It is, but it's also CH arrows, a molecule that's fundamental to, the metabolism of almost every living thing.
And that's what this deep dive is all about. We want to unpack its really sophisticated roles. It's not just for making things tart.
Not at all. It's a master pH regulator, a
Yeah.
flavor enhancer, and it has this secret job as a metal sequestrant.
So our mission today is to trace its journey, right? From squeezing lemons by hand to this huge biotechnological process.
And then we have to get into the new clinical debate around the manufactured form. It's a fascinating story.
Okay, let's unpack this. Let's start with the history.
Awesome.
Before we had these giant fermentation vats, where did citric acid even come from?
Well, for centuries, the only source was citrus fruits, lemons and limes.
Just lemon.
Just lemons, basically. If you go back to the 18th to 19th centuries, all commercial citric acid was manually extracted from lemon juice, which is, maybe 7 to 9% citric acid.
Wow. And a guy named Carl Wilhelm Scheele, he pioneered that back in 1784.
That's right. He figured out the first real extraction method. But you can imagine the problem.
Oh, I can. You're completely dependent on the lemon harvest.
Exactly. It was a logistical nightmare. The cultivation costs were huge. You had seasonal ups and downs, the shipping. It was just spectacularly unsustainable as industrial demand started to explode.
Nature just couldn't keep up.
It couldn't scale. The whole system was hitting a wall.
So this is where science has to step in. How do we get from a lemon grove to a lab?
The first hint came in 1893. A German botanist, a guy named Wiemer, he noticed that a certain mold, penicillium, could actually produce citric acid from sugar.
Okay, so the idea was there.
The idea was there, but it wasn't really a commercially viable process. It was hard to control.
So what was the real breakthrough?
The real game changer came in 1917 from an American chemist at Pfizer, James Curry. He discovered the incredible efficiency of a specific fungus, Aspergillus niger.
Wait a second, Aspergillus niger. Isn't that just common black mold?
That's the one. The same stuff you might find in a damp basement. It's everywhere.
And he figured out how to use it.
He figured out that if you control the fermentation conditions perfectly, the sugar, the temperature, you could get this common mold to just churn out massive amounts of citric acid.
And Pfizer jumped on that.
They did. They started industrial scale production in 1919, and it just completely displaced citrus extraction. The cost plummeted, the supply was constant.
So today, pretty much all of it is made this way.
About 99% of all citric acid on the planet comes from this microbial fermentation process.
That's incredible. Okay, so that sets the stage. Now let's get into why it's so important. What is it actually doing in our food?
It really comes down to two main pillars, safety and quality. And to understand that, you have to look at the chemistry. Right. It's an alpha hydroxy acid with 3 carboxyl groups. That's the key. Being polybasic, it means it can donate 3 protons.
And having those 3 points of ionization, the 3 pKa values, that's what makes it such a good preservative.
Precisely. Its pKa values are 3.13, 4.76, and 6.39. So think of it like this. Most acids get 1 shot to buffer the pH. Citric acid gets 3.
So it can stabilize pH over a much wider range?
It's a surprisingly wide range.
Yeah.
From a very acidic pH of 2 all the way up to around 8. It's incredibly robust.
Let's talk about the first pillar then, safety. The botulism barrier. How does it stop one of the deadliest foodborne pathogens?
It's all about getting the pH of the food below a critical number, 4.6.
Okay.
When you're canning something like tomatoes, you have to get below that threshold to stop the spores of Clostridium botulinum from germinating and growing.
So the acidity itself is the barrier.
It is, but the way it works inside a microbe is the really elegant part. It's like an internal metabolic siege.
A siege. Okay, explain that.
So in that acidic environment, below 4.6, the citric acid molecule is mostly undissociated. It's uncharged, lipophilic.
Meaning it can slip right through the cell membrane of a microbe?
Like a secret agent, exactly. It gets inside the cell where the environment is neutral, around pH 7.
And then what?
The molecule instantly dissociates. It releases a flood of protons inside the cell.
Ah, so it acidifies the microbe from the inside out.
It does. And the microbe's defense systems, these little proton pumps, have to work overtime, burning massive amounts of energy just to pump those protons back out and stay neutral.
So you're not poisoning it, you're forcing it to run itself to death.
You've got it. It just runs out of fuel trying to maintain balance. That leads to stasis or cell death, a very effective kill mechanism.
That is brilliant. Okay, safety pillar, lockdown. What about the second pillar, quality? You called it a secret chelator.
Right, chelation. This is its silent quality control job. The word comes from the Greek for claw. The citric acid molecule literally acts like a tiny chemical claw.
A claw for what?
For grabbing onto metal ions, specifically polyvalent metal ions.
So we're talking about things like trace amounts of iron or copper in food.
Exactly. Iron, copper, those are the big troublemakers. In any food with fat, like margarine or ground meat, those metals act as catalysts that speed up oxidation.
Which is what causes rancidity, that off flavor.
That's the one. So citric acid comes in, wraps up or chelates those metal ions and just takes them out of the equation. It renders them inert.
And that extends the shelf life.
Dramatically. But it also works on color.
Preventing browning in apples and things like that.
Precisely. That browning is caused by an enzyme, polyphenol oxidase, or PPO. And PPO needs copper ions to work.
So citric acid pulls a double duty here.
It's a fantastic two-pronged attack.
Huh.
First, it lowers the pH on the fruit surface, which slows the enzyme down. And second, it chelates the copper that the enzyme needs as a catalyst.
It robs the enzyme of its tool.
It does. Dual inhibition, a masterclass in food chemistry.
It really is. Okay, let's circle back to Aspergillus niger. How do manufacturers get it to make so much citric acid? You said it's about engineering its metabolism.
Right. So in nature, the fungus makes citric acid, but it's just one step in its energy-producing cycle, the TCA cycle. It makes it and then immediately consumes it.
The TCA cycle, that's the cell's engine, right?
The central engine, yes, where it makes ATP. So the industrial goal is to create a metabolic traffic jam, a bottleneck.
So the citric acid just builds up with nowhere to go.
Exactly. They do this by inhibiting the next two enzymes in the chenoconitase and isocitrate dehydrogenase. When those are blocked, the citric acid accumulates and the fungus is forced to just excrete it.
That must be an incredibly delicate process to control. The sources mentioned trace elements being key.
It's balanced on a knife edge. They have to be incredibly strict about manganese, for instance.
Why manganese?
Because even tiny amounts of manganese tell the fungus, hey, conditions are great, let's focus on growing bigger. And it will grow, but at the expense of producing citric acid.
So you have to stress it just the right amount.
You have to starve it of certain nutrients to force it down this overflow pathway where it pumps out the acid you want. It's amazing control.
And it rarely works alone, right? You mentioned it's a potentiator.
It's the ultimate team player. Take other common preservatives like sodium benzoate or potassium sorbate.
E211 and E202.
Those are the ones. They're only really effective in their undissociated form.
Yeah.
Which means they don't work well in foods with a pH above 4.5.
They're just dormant.
Mostly. But you add a little citric acid, drop the pH below 4.5, and suddenly the vast majority of those benzoate molecules become active and effective.
So you can use less of each individual preservative.
Exactly. It's a synergy. The combination is way more powerful than the sum of its parts.
Okay, before we get to the modern debate, we have to clear something up. The benzene issue in soft drinks. People often blame citric acid.
And that's a really important distinction to make. Yes, benzene, a carcinogen, can form in some beverages.
Right.
But the reaction is specifically between sodium benzoate and ascorbic acid vitamin C.
Not citric acid.
Absolutely not citric acid. It doesn't have the right chemical pathway to cause that reaction. It's a common point of confusion, but the science is very clear on it.
Good to clarify. All right, let's get into the most nuanced part of this. The clinical debate. The paradox.
Yes.
Natural citric acid from a lemon and manufactured citric acid, or MCA, from the mold. They are chemically 100% identical.
Identical.
Yet some people have severe adverse reactions only to the manufactured kind. How is that possible?
It is a genuine scientific puzzle. The best look we have at it comes from some 2018 case reports by Swice and Cressy.
What did they find?
They documented 4 patients with these recurring severe inflammatory symptoms. We're talking severe joint pain, muscle aches, bloating, fatigue.
And it was linked to manufactured citric acid.
Specifically linked. When they consumed products with MCA, supplements, energy drinks, the symptoms flared up. When they removed MCA, the symptoms vanished.
And crucially, they could eat lemons and limes with no problem.
No reaction at all to the natural form. Which leads to the main hypothesis.
Which is?
That the reaction isn't to the citric acid molecule itself. The theory is that it's a reaction to trace impurities. proteins or other metabolites from the Aspergillus niger mold that might survive the purification process.
Because that mold is a known allergen, so even tiny fragments could trigger an inflammatory response in someone who's sensitive.
That's the working theory. Now, in fairness, we have to bring in the industry's counterargument.
Okay.
They point out that the purification process is incredibly rigorous. You've got heat, filtration, activated carbon treatments, crystallization. It's all designed to get to 99% purity.
So they argue the chances of significant mold proteins making it through are slim to none.
That's their position. They also note that the symptoms being reported, the joint pain, the edema, they aren't your typical immediate allergic reactions involving histamine.
So it's something more complex than a standard allergy if it is happening.
Yeah. Exactly. It points to a more nuanced immunological sensitivity.
And this whole debate is pushing some manufacturers to look for alternatives, right?
It is. You're seeing a real push for clean labels. Some companies are exploring other microbes, like the yeast Yersinia lipolytica, to make citric acid. The idea is to use a different biological source that might have a different, maybe less allergenic profile.
So wrapping this up, where does this leave us? We've gone from lemons to labs, from botulism to browning.
And I think what's clear is that citric acid is still, without a doubt, the most important organic acid in the food industry. For safety, it stops pathogens. For quality, it stops rancidity and discoloration.
It's the silent workhorse in our pantry. But as we finish up, I want to touch on what's next. The source material mentioned a really interesting intersection of sustainability and technology.
Oh, this is the exciting part. The future is about upcycling.
Upcycling.
Yeah, specifically using solid-state fermentation, or SSF. Instead of feeding the mold pure sugar, researchers are now growing a niger on agricultural waste.
Like what?
Things like used kiwi peels, corn cobs, apple pomace, things that would normally be thrown out.
So turning food waste into a high-value food additive.
And it's incredibly efficient. Some studies using kiwi skins have produced as much as 100 grams of citric acid per kilogram of waste.
Wow.
It uses less water, creates less wastewater. It's really the perfect way to balance that industrial efficiency we need with a much, much smaller environmental footprint. It's a pretty brilliant next chapter for the invisible architect of our food.